Good day, everyone. I am Joseph of Digilytic Solutions. I am a consultant, trainer, speaker, and a book author. Welcome to our course, Deep Learning Mathematics. In this lesson, we will learn about how to analyze identity and inverse matrices. At the end of the lesson, you are expected to identify identity and inverse matrices. Follow the process of understanding identity and inverse matrices and appreciate the uses of identity and inverse matrices in deep learning. In our last lesson, we learned about how to multiply matrices and vectors. We learned that multiplication is one of the most important operations involving matrices. With that, we said that in A times B equals C, A is one matrix and B is another. The product C is also another matrix. We discussed that for C to arrive at certain requirements must be followed. One is that A must have the same number of columns as B has rows. The second is that if A is of shape M by N and B is of shape N by P, C should be of shape M by P. We also talked about the dot product and Hadamard product. So if you missed lesson number 4, the link is given in the description below. Linear algebra gives us a very powerful tool that allows us to solve the equation Ax equals B for a number of values of A. So this tool is called matrix inversion. However, this tool cannot just be used indiscriminately. So to understand this concept of inversion, let's define the concept of identity matrix first. So identity matrix is a matrix that does not change any vector when we multiply that vector by that matrix. Does it sound confusing? Have some patience because we will walk through step by step. So treat it like when you face a mirror. So is that face you see in the mirror different or the same? Of course it is the same. So it is still the same face. It is your face. Why? It is because it is your identical face. Is that clear? So that's the concept of identity matrix. So the IN, let me write here. Okay, IN refers to the identity matrix that preserves n-dimensional vectors. So let me repeat that. IN, which means identity matrix, refers to the identity matrix that preserves n-dimensional vectors. So when we say n-dimensional again, it's the number of the columns or the rows. So in identity matrix, the number of rows and the number of columns are preserved. So if it's 2 columns and 2 rows, let me write this one again. 2 rows and then 2 columns in the original, then in the identity it is also 2 by 2. So this is the original, this is the reflection or the identity matrix. So that's it. So another interesting fact about a matrix is its structure. Now, the structure of an identity matrix is that all of the entries along the main diagonal are 1, while all the other entries are 0. So, oops, I got a mistake here. So it is supposed to be 1. Okay, so this is the structure of our identity matrix. So this is the diagonal, and the numbers in the diagonal are 1, and the others, the sides here, must be 0. So how is an inverse denoted? The matrix inverse A is denoted as A, then there is -1. It's like an exponent, but it's not actually an exponent. It is superscript. And it's defined as the matrix such that A, -1, A, this is the original, is equal to the identity matrix, which means when we're going to multiply the identity matrix and the inverse matrix and the original matrix, then the result would be the identity matrix. So again, the -1 here means that A1 is the inverse of A. So later in our example, we will have a concrete understanding about that. Okay, so do you still remember about reciprocal? We had that in our elementary math, reciprocal. Okay, so for example, the reciprocal of 9 is 1/9, such that when we multiply 9 and 9, it becomes 1. Okay, so the idea behind the inverse is the same idea with the reciprocal. Okay, so such that again, when we multiply this and then this one, the result is 1. So after knowing what the inverse is, so we can now solve for ax equals b using this step. So this is the step that we're going to follow when we're going to solve for ax plus b or ax equals b. So ax equals b, then the next step is that the inverse of a is equal to a, again it's inverse, then b, identity x equals a inverse b, x equals inverse a, then b. So later we will have that, how it is done with real numbers. Oops. Okay, so this process may depend on the possibility of finding a -1. So in our future lesson, we will discuss about the conditions for a -1, this one, the inverse of a, to exist, so that do not forget to subscribe and hit the bell button below for your notification of our next lesson. So maybe at this point you would like to ask if it is the same idea with the reciprocals. So why is it that we cannot do 1/a? Right? It's a very good question. Again, let me repeat that. Why is it that we cannot do 1/a if the same idea with the reciprocal and the inverse? Okay, so well, the answer is that we do not divide by a matrix. Again, we do not divide by a matrix, because when we multiply a matrix by its inverse, we get the identity matrix, which is like 1. Okay, let me repeat that. When we multiply a matrix by its inverse, like this one, when we multiply the matrix by its inverse, then the result is its identity matrix, which is like 1 of the reciprocal. So the output would still be the same. So aside from the fact that an identity matrix has ones in the diagonal and zeros everywhere else, it is also square, right? Square. It is also square, which means that it should have the same number of rows as columns. So how many columns do we have in here? We have 3, right? So 1, 2, 3. Then how many rows? 1, 2, 3. So this must be square. So this is another property of identity matrix. So again, there should be the same number of columns, and there should be also the same number of rows. So in this case, we have 3 by 3. That's why it is a square. Okay, now, the next question is this. How are we going to calculate the inverse of a matrix? So, let's have this. This is actually the process of doing the calculation for the inverse. And how do we do this? Now, let's examine this one by one. So here, we swap the positions of A and D. So again, this is our original. Then we put here -1 to mean that we're going to find the inverse of this matrix. So what we do here is that we swap D, T, and A. So here, the D here, which is at the bottom right, it becomes the upper value at the upper left. Okay, then B and C, we just add negative sign before them. Okay, then after that, we divide everything by the determinant. So how do we get the determinant? It's just very simple. You only have to follow this arrow. Okay, that means we're going to multiply first AD, here AD, and then B and C. So it's like letter V. Do not forget letter V. V. So V first, this way, and then after that, this way. So you will never get lost. Okay, so after that, we divide everything by the determinant. So it means D divided by the determinant B, or negative B divided by the determinant, and so with C, or negative C, and also with letter A. So let's consider this example. So we're going to have a concrete understanding of what this one is. So we're going to find the inverse of this matrix. So our original matrix is 2, 4, 1, 3. So we're going to find for its inverse. So how we're going to do that? So again, the first step is that we're going to swap the positions of these numbers. So before, the 3 is here, now we have it here. Then 2, of course, excuse me. And then we're going to put the negative sign for 4 and then 1 here. And remember letter V to find the determinant. So we multiply 2 and 3, and this gives us 6. And then we multiply 4. Okay, sorry. It is supposed to be 4 and 1. 4. This is a mistake. Let me write here 4 times 1. Okay. 4 times 1. Okay. So 4 times 1. 4 times 1 becomes 4. So that means 6 minus 4. And that gives us 1/2. Now, we are ready for the calculation. So if we're going to calculate 3 divided by 2, we will have 1.5. Negative 4 divided by 2, or 1/2 times negative 4, that gives us negative 2. 1/2 times negative 1, this gives us negative 0.5. And 1/2 times 2, that gives us 1. Okay, so this one is actually our inverse. So this is the inverse of this matrix. Alright, so now the question is that how are we going to prove if our answer is correct? Would there be some kind of solution for us to check that this one is correct? Okay, of course there is. So this time we're going to check if this solution is correct. And how are we going to do that? Do you still remember? Where is it? Let me go back. Okay. I think I put it. Okay, this one. Okay, so if we are going to multiply this inverse to this, then that gives us the identity. And remember our identity? This one. Okay. Right? But then, it's because we have only 2 rows And in 2 columns, expect that we will only take note of this picture. Okay, so there should only be 2 columns and then 2 rows for our identity matrix. And how are we going to do that? Okay, now let's find out. Okay, so here it is. So let's write first the original matrix, that is 2, 4, 1, and 3, and then let's multiply that with its inverse, which is 1.5, negative 2, negative 0.5, then 1. Then remember our multiplication before? So this is 2 times 1.5 plus 4 times negative 0.5. So it's like this here and then here. Okay, and then for the second part, what we'll do is that this one to this and this one to this, and of course we're going to repeat the process for the lower terms. Now if you're going to do the process of multiplication and then addition, then we will get to this. So if you're going to multiply 2 times 1.5, we will have 3. Then 4 times negative 0.5, we'll have negative 2. And then here, 2 times negative 2, that gives us negative 4. And 4 times 1, that becomes 4, of course. And then we will do the same process for the lower terms. So 3 minus 2, that gives us 1. Negative 4 plus 4 is 0. 1.5 minus 1.5 is 0. Negative 2 plus 3, that is 1. So now let's go back. Is it? Oops, is it lost? Okay, it's here. So right now let's examine. Our first term here is 1. This is 1. Okay, then here it's 0. Then we have 0 here. Then 0, 0, then 1 is here. So are they the same? Yes, they are the same. So we have ended up with identity matrix, and our solution therefore is correct. So this is check. Why do we have to study this? What is this for? If there is a negative 1, a number of different algorithms also exist to find it in closed form. A negative 1 is very useful as a theoretical tool. It may not be used in practice for many software applications. Because it can be represented with a very limited precision on a digital computer, it means that algorithms that make use of the value of b can arrive at more accurate estimates of x. Inverse is also used to calculate parameter vector binomial equation in linear algebra. So after all being said and done, let's try this. What is an identity matrix? Then find the inverse. Be sure to check your answer. So we have the matrix 4, 7, 2, 6. Comment down your answer below. Do not forget to subscribe, like, and share. Please click the bell button to be notified every time we have a new session. See you in the next lesson.